Hi everyone, I'm Varsha Swami and I'm an undergraduate student at State. I investigated the mineral precipitation and dissolution during carbon sequestration under the guidance of my thesis advisor, Dr. John Hooker. So carbon sequestration is a geoengineering technique to store away carbon dioxide in the subsurface. This has shown a lot of potential in Reykjavik, Iceland, where they had a successful experiment in 2012. In the pilot phase study, CO2 emissions were turned into solid mineral by storing it deep underground in basaltic rock formations. Over 95% of the CO2 mineralized over a time span of 2 years. With carbon sequestration, two reactions are prominent: dissolution and precipitation. Precipitation is ideal and the end goal, but both are likely to happen in the pores of the rock. The main concern is that we inject CO2 into the subsurface, and the CO2 plugs up the pore space and the reaction stops after minimal mineralization. By causing deformations, we can increase the surface area, which allows for more carbon storage and increases the efficiency process overall. This study's primary objective is to understand how the subsurface rocks respond to fluid injection using laboratory precipitation and dissolution. There are two sets of experiments: CO2 experiments shown on the left and sandpack deformation experiments shown on the right. The CO2 experiments reacted olivine, carbon dioxide, water, and an acid or base. The three main acids and bases used were citric acid, acetic acid, and baking soda. The acid and base were used to help the reaction occur at laboratory conditions, as well as to increase the ionic strength of the solution. The sandpack deformation experiments used salt as an analog for olivine dissolution and carbon precipitation. In these experiments, parameters such as grain size, the way sediment was deposited into water, and the heterogeneity of the sediment pack was varied. For the CO2 experiments, mass was collected before and after the experiment to track how the mass changed. The x-axis here shows the mass at the beginning of the experiment. The y-axis shows the mass at the end of the experiment. A total of 10 experiments were completed and plotted. They were fitted on a one-on-one line to show a visual representation of the mass gain and loss. Any data point above the line indicates a mass gain, while anything below indicates a mass loss. Acetic acid experiments had a mass gain, while all of the other experiments that involved baking soda and citric acid had a mass loss. To assess deformations, ImageJ, a software from the NIH, was used. Measurements such as angle, length, area, and perimeter were gathered and compared over time. This figure is the ImageJ analysis of the area of 5 caves tracked over time. The x-axis is time in days, and the y-axis is the area in centimeters squared. Over time, we see that the caves had severe fluctuation in area and was inconsistent in growth. A paired t-test was done for the sets of data, and most yielded statistically insignificant changes. Comparing cave growth over time, we see that it's evident that the cave growth happens within the first few weeks of removal. The number of caves also increase over time. In the precipitation experiments, the initial and final size of halite crystals were compared. In conclusion, this research helped to get a better insight of what goes on in the subsurface with dissolution and precipitation. The precipitation experiments showed an evidence of halite crystals growing in size and pushing outward to create more pore space. The dissolution experiments showed an increase in the number of deformations and no statistically significant change in cave dimensions over time. Using acid helped the reaction to occur in laboratory conditions for the CO2 experiments. I want to thank Dr. Peter Haney, Athena C. Chen, and Denny Wallitzer for the use of lab materials and storage at Penn State. Thank you for your attention, and I look forward to seeing you at the live conference.